This is our third and final video lecture on electrochemistry, and this one is going to focus on electrolytic cells. An electrolytic cell is essentially a galvanic cell run in reverse or run backwards by applying an electrical current to drive a non-spontaneous reaction. If you think about your cell phone, you use it, the battery in there is functioning as a galvanic cell. It's providing a current. The meter tells you it's time to charge it again, you plug it in, and now you run that same reaction in reverse, backwards. Now that battery is functioning as an electrolytic cell as we're pushing that battery, as it were, back up the hill so it can provide you with another day's worth of service. Electrolysis is using an electrolytic cell to accomplish a chemical purpose, so the production of some material using an electrolytic cell. And a couple of examples of that we might look at are gas production. Here we can put water under electrolysis and generate hydrogen and oxygen gases, or electroplating, where we can apply electricity to some sort of solution, or in this case molten sodium chloride, and produce a metal. It's the latter of these two electrolysis applications that we're going to focus on, looking primarily at the electroplating of metals. Now, here is a basic reduction for a metal ion. So now we're talking about a metal ion in an aqueous solution. So here is some metal N, M, with a charge of N+. So our equation is M, N+, plus N electrons is going to give us M, the element, or just the pure metal. So we can look from this that it's going to take N moles of electrons to produce 1 mole of the metal. We're also going to need to introduce Faraday's constant here, which is the charge, coulombs, of 1 mole of electrons, and that number happens to be 96,485. Now remember, as always, we're not going to memorize numbers in this class unless we just have to. You can have access to that number anytime that you need it. Then we need to consider current, which is how fast the electrons are flowing. This is measured in amps, where amps and coulombs are related by this relationship. 1 amp times 1 second equals 1 coulomb. And finally, we have our old friend molar mass, which is grams per moles. If we put all that together, we get this very important equation that I've got in the box here, that the mass of metal plated is equal to current times time times molar mass divided by N times F, where all of our terms have been defined above. The important thing for you to note here, looking at this equation, is that the larger or the higher the current, the more mass plated we have. The longer the time, greater T is, then the more mass of metal that we can plate. Here again is our equation for mass of metal plated. And let's notice that if I know any two of the three, current, time, or mass plated, then I can easily calculate the third. Notice that the others are fixed quantities. The molar mass, we're just going to look up the molar mass of the metal on the periodic table. Faraday's constant is constant, and N is going to be known as soon as we know what metal it is we're plating out from what particular ion in solution. We could actually use electrochemistry to determine what this oxidation state was. We won't be doing that in this class, but it's certainly an application. Let's look at 3 quick examples. The first one asks the question, what mass of silver can be plated from a solution of silver nitrate using a 2 amp current for 30 minutes? Well, again, what do we need to know? We need to know the current, we need to know the time, and we need to know the number of electrons needed to plate out silver. The current is given at 2 amps. The time is given. It's 30 minutes. We're going to multiply by 60 seconds per minute, so that means my time is 1800 seconds. And N now is going to be 1. In this case, our chemical knowledge is that the only stable oxidation state of silver is the +1 state, so that means it's going to take 1 electron. So the mass of silver is going to be I times T times the molar mass divided by N times F. And if we simply plug those numbers into a calculator, we find that we're going to generate 4.03 grams of silver. We've simply taken the equation at the top, plugged in what we know, and solved for what we don't know. Here's a second example asking a different question. What current is needed to plate 10 grams of gold from a solution of gold 3 acetate in exactly 6 hours? In this case, we need to know, to find the current, we need to know the mass of the gold, that's given at 10 grams, the time in seconds, that's given, 6 hours, 60 minutes per hour, 60 seconds per minute is 21,600 seconds, and N. Here, N is explicitly given by the name of our compound. That's gold 3 acetate, so we know that gold is in the +3 state, so N is going to be 3. So now we're going to plug in. There is the mass of metal plated. There is the time in seconds. Remember, our time has got to be in seconds for our units to work out. There's the molar mass. There's N, and there is F. Performing the math lets me know that 10 grams is equal to I times 14.7, or I is 10 divided by 14.7, and we need a current of 0.680 amps. Again, if we know 2 out of the 3 of mass, current, and time, we can easily solve for the third one. Here's our third and final example, and this is going to be one where we're asking about time. What time is needed to plate 10 grams of nickel from a solution of NiCl4 using a 1.25 amp current? Again, what do we need to know to calculate time? We need to know the mass of nickel, that's given at 10 grams. We need to know the current, that's given as 1.25 amps. And N is also given. NiCl4, again, our chemical knowledge tells me that Cl comes in the Cl-1 form, so that means nickel is +4, so N is equal to 4. Plugging our numbers in then, look, there's my mass, there's my current, time is what we're solving for, molar mass, N, and Faraday's constant. That means that my mass is going to be time times 1.901 times 10 to the -4th, or time is 10 divided by 1.901 times 10 to the -4th. And time solves to be 52,600 seconds. That's roughly speaking 875 minutes, or a little more than 14.5 hours. So using a current of that magnitude to weigh out 10 grams is going to take approximately 14.6 hours. This concludes our discussion of electrolysis and concludes our discussion of electrochemistry.